Hello, good morning, and welcome to the School of Mathematical Sciences at the University of Southampton. So I am Professor Marika Taylor, the head of the school, and I'm going to talk to you today about some of the research and some of the work that we do with business and industry. So the title of this talk is The Science of Stephen Hawking. So Stephen was interested in using mathematics to answer very big questions about science, but also big questions for society too. So a brief history of Stephen. Well, perhaps the thing that you might sort of think of him immediately when you hear his name is his famous book, A Brief History of Time, written in the mid-1980s. He was born in 1942, and very early on in his academic career in 1963, he was diagnosed with ALS, motor neurone disease. And this was something for which the prognosis at the time looked very, very poor. And yet he went on to sort of confound all expectations and live for, a very, very long time. He was the Lucasian professor at Cambridge for 30 years. So the Lucasian professorship is the chair that was held by Isaac Newton and has been held in between Isaac Newton and Stephen by very, very famous scientists. And this book, A Brief History of Time, this was the thing that I think really launched Stephen to, worldwide recognition. That came out in 1988. He died sadly 2 years ago in March 2018. Obviously very sad his death, but still absolutely amazing to live to the age of 76 with such a serious health condition, and not just to live, but actually to carry on and be a sort of, a prolific scientist. He was working up to the moment of his death, and also he was advising governments. He was, active in outreach for science, trying to engage people from all parts of the world to come into science. Just an absolutely amazing person. So here's some pictures of him. So there is, pictures you may all recognize. The left-hand picture is Stephen and the person who played Stephen in the movie A Theory of Everything. I mean, it's quite amazing, that movie. When you know Stephen, as I do, I was a student with him. When you know him, it's quite amazing how the kind of behavior and facial expressions were captured in that movie. In the top right picture, you can see Stephen. So Stephen loved sci-fi shows. He loved comedy shows. He was very, very proud of having been in Star Trek, and he was also very proud of being in The Big Bang Theory. So you see here him advising Sheldon about his theories. I think this is one of the episodes where he tells Sheldon that his theories are absolutely wrong. And another thing he was very proud of, you can see at the bottom right, a picture of him in The Simpsons. Again, so proud of that. He had these pictures on the wall, and he used to send Christmas cards with him as the Simpsons character. So amazing sense of humor. So as I said, I was a student with Stephen, so I worked in Cambridge with him for about 6 or 7 years. And I've been involved in working on his final book and launching his final book. So it's called Brief Answers to the Big Questions, and it really talks about questions in science and questions in society. The latter half of the book is really talking about how science plays a vital role in addressing the sort of big challenges that the world is facing. So climate change, famine, disease. And it also talks about how artificial intelligence, and I think more generally than that, data science as a whole, may impact on our future. Sometimes Stephen was quoted as saying that, we should be terribly afraid of AI, we should be afraid of data science. I think that's a misquote. What he was really saying is that we should actually be prepared for it in a way that we were perhaps not prepared for the web changing the way that we behaved as it came into play in the 1990s. He really wanted society to actually think about how things will change and what the ethical issues will be, the questions of other parts of the world being left behind. He thought that we should actually have a conversation about those things and actually engage the public. So what's the aim of this talk? So the questions that are posed by Stephen Hawking in that book really relate very closely to the work that we do in Southampton mathematics. So our research is spanning both fundamental science and applied collaborative projects, often done in association with businesses, with industry, finance, government agencies. Now, you may be used to thinking of these things as very, very distinct, very separate, areas. But actually the mathematics, the mathematical science techniques that are used, often very deeply entwined with each other. You might use similar types of mathematical techniques to forecast both the evolution of the universe, so one of Stephen's sort of questions, big questions in science, and much more down-to-earth things like trying to understand changes in stock prices. So in fact, many people who work and do research, as graduate students in areas of mathematical physics, often go and work in finance companies. They're highly sought after to actually go and work in hedge funds because the mathematics that's used is so similar. In fact, one of the most successful hedge funds in the world, the Renaissance hedge fund, which is run by Jim Simons. Jim Simons was a mathematical physicist. In fact, he still is a mathematical physicist, but at some point, decided to sort of step aside from academia, take some ideas that he had and start up a hedge fund. If you kind of take a Google of that, you'll see that Renaissance is one of the highest performing hedge funds. They're using some of the most sophisticated mathematical modeling techniques, which are borrowed from mathematical physics. So we're going to go on to a journey now, and we're going to start with the fundamental science. I should say that I have some bias here because this is my own group's particular interest. But I think these are, I think it's the kind of questions that we all ask, and it's questions that we all ask, particularly when we're younger. And it's kind of nice to see where the science is actually getting to at answering this. So the title of the movie that I referred to before, the biographical movie about Stephen and his first wife, Jane Hawking, it had a title, The Theory of Everything. And of course, the theory of everything, that's a way of sort of phrasing what Stephen was trying to do in his scientific career. So the kinds of questions he was trying to answer were things like, how did the universe begin? How can we predict the future of the universe? Then there are things like I told you that Stephen loved science fiction. And for those of you who love science fiction, time travel and wormholes, they play a big role, right? So they're often used as part of the plot. Is this science fiction or is it fact? Well, I'm not going to go too deeply into this here. That's another talk. But, it's somewhere in between. It's certainly science fact, but at the moment, we don't actually know how to build these. I think it's, 100, 200, 300 years in the future that we can actually see a way to actually construct a wormhole, and probably even further in the future to actually do anything constructive with it, like move forward in time. In any case, a theory of everything, the idea is that could actually try and answer these questions. And that for Stephen was his sort of holy grail. That was what he wanted to do. Now, as I said, I mean, this is a question which human beings have asked since, since the beginning of time. So really from ancient times, people have wondered about the origin and the development of the universe. And we may all be aware of some of the ideas that, ancient societies had. So what's shown in the picture here on the right-hand side is the ideas that came from Hebrew cosmology, the idea that the universe is the heavens, the earth, and the underworld, and they had names for all of these, and they had ideas about how they came to be. Another great sort of ancient sort of societies, of course, the Chinese societies thought about ancient cosmology also. And Pangu is considered, the first living being in the creation of the universe in some versions of ancient myths. I believe he's often shown holding the yin-yang symbol, representing the complementarity of opposite or contrary forces. Now, it's really quite remarkable. This same symbol is actually often appearing as part of our modern scientific understanding of the quantum universe. So I'll come to this a little bit later. But again, this idea interpreted in a modern scientific way, that there is a certain complementarity of forces which seem to be either opposite or contrary or different to each other, that actually comes into our modern understanding. Now, as we move forward in time, humans start to understand that the Earth is not at the center of our solar system. They understand that there's really a solar system and the Earth is at the center. So we move to an era of heliocentric cosmology. As many of you know, this was obviously a very controversial thing in Europe, with many people, the Christian church, challenging this notion that the sun could be at the center and the Earth wasn't at the center. But in this, in the heliocentric cosmology, we have moved away from the Earth being at the center. But even once people had done that, there was a reluctance to accept that the universe itself might actually be changing in time. There was still this sort of clinging idea that the universe wasn't actually changing with time. And I always find fascinating that in the 19th century, in biological sciences, we accepted that organisms were evolving. Of course, it was controversial, and there are parts of the world in which it's still controversial, but the basic idea of Darwin that organisms evolved was really accepted by the end of the 19th century. At the same time, people were still clinging to this idea that the universe as a whole was not changing in time. That the positions of the galaxies was not, the positions of the solar system, the galaxies were not changing. There was no, substantial change in time. And it was really only in the 20th century that people came to accept that actually the universe was going to change with time. Something that I think we all accept now. We all know in our sort of colloquial vocabulary, we've heard of the terms Big Bang Theory. Even if we haven't, even if we only get it from the TV show, we get the sense that it's referring to the fact that the universe is changing in time. So our understanding, our modern understanding, starts with Albert Einstein, a picture I guess that all of you are familiar with, and it starts in 1915. So it's at that time that he introduced a new theory of gravity. It's really the first new theory for 300 years. It supersedes Newton's theory because it applies even when gravity is very, very strong. It's trying to describe sort of effects of very, very heavy objects or things which are moving very fast. And the basic idea of this, I'm not going to go into any details of it, is that the space and the time are understood to be shaped by what's in the universe, the matter and the energy in the universe. So it's very profound concepts. Perhaps you can get a sense of why this is studied in the maths department, because when I start talking about things being shaped, you understand that it's a theory that relies on geometry. In fact, when Einstein wrote it down, very few people in the world understood the mathematics of this theory. It was really mathematics that was only known and understood by specialist mathematicians. Now, the idea, as I said, is that the things which are heavy will actually curve the space which is around them. And this is often shown in pictures in terms of the space-time being represented by a grid, and the grid being kind of shaped by the heavy objects. So something like the Earth, which is heavier than the Moon, will actually curve the space around it much more. Now, of course, once you had this theory of gravity, it was natural to think, not just the solar system, but the universe as a whole. What does it imply for galaxies? That people knew already at the beginning of the 20th century that the solar system was part of a bigger galaxy. They could look up in the sky, and they'd even realize that our galaxy was not unique. Now, as I said, there was this huge reluctance to accept that the universe itself should be changing with time. Einstein actually famously tried to fudge his theory so that he could get the universe to be unchanging in time. But, as a theorist, you always have to confront eventually experiments, and he was proved wrong. He was proved wrong by Edwin Hubble, again, a very familiar name. So Edwin Hubble took a telescope in California up on Mount Wilson, and he basically showed that the universe was expanding. So that the plot that you're seeing there is really the plot that sort of demonstrated that if you looked at things which were in the past, they were actually closer together. So galaxies have actually moved, are moving apart from each other. The universe is actually expanding. And this was, incontrovertible evidence. Confronted with the evidence, Einstein had to kind of change his theory. And so, people accepted, the idea that, the universe was actually really changing with time. So where does Stephen come into this story? So, as I said before, the mathematics of Einstein's theory is really very, very complicated. Understanding that mathematics was almost put on hold because of global politics in the 1920s, 30s, 40s. People were concentrating very much on nuclear physics. They were developing the understanding which led to the atomic bomb. Many scientists were actually, being displaced, having to move from Europe into America. They were starting up their labs again. They were working on things, relevant for the Second World War. And so there wasn't a lot of study of Einstein's theory. But as we move into the 1950s and 60s and we move into the global space race, people started to literally look up in the sky And they started sort of thinking about gravity again. I keep saying that fundamental science is often, entwined with applied science. So there were people who were funded in the great, departments in Princeton and Harvard to be doing things for the military in terms of space science, but they kind of found themselves actually trying to understand Einstein's theory of relativity. And so there was really a renaissance of people studying it as we go into the 50s and 60s. So Stephen Hawking, in the beginning of the 1960s, he was a graduate student in Cambridge, and he was really interested in analyzing Einstein's theory in the context of cosmology. And he hooked up with the famous mathematician Roger Penrose to develop techniques to analyze Einstein's equations. So again, it was really very sophisticated mathematics. And what they showed conclusively, really, is that the beginning of the universe was very small and very hot. So it's not just that the universe is now expanding. It means that if you look back in time, it was much, much smaller. And what they showed is that it just kept getting smaller and smaller. There was no sense in which, it just stabilized at some size. It just got smaller and smaller and smaller and hotter and hotter and hotter. And it's really around that kind of period that people start coining the idea of a Big Bang. So when we draw this picture, so this was drawn for us actually from my research group by a very talented artist, Oliver Dean. This sort of symbolizes really the change in the universe in time. So time is shown on the horizontal axis. And what you see on the right-hand side is what you look up and see in the sky now. You see galaxies. But as you go back in time, what this funnel is showing is that the universe was much, much smaller. And the change in color is illustrating for you the fact that it's getting hotter. In the middle is a sort of, a slightly grainy picture, which I'll explain in a moment. And as you go to the very far left, it's getting kind of fuzzy. Well, the fuzziness represents our lack of understanding, and actually also something in physics. It represents that there's quantum physics going on as well. So I'm not going to go into the detailed mathematics of the scientific theory of the universe. But what do we really mean when we talk, when I keep using the phrase, a theory of everything, a theory of the universe? What we really mean is a mathematical description of the physical laws, which makes predictions for observations. So the thing that's shown on the right-hand side of there is some equations which describe the evolution of the universe. The parameters there that you see are actually the parameters that describe the universe. But then you could say, well, there's a basic problem, surely. So this is the great theory, but how on earth can we observe something that took place billions of years ago? The universe is about 13 billion years old. How could we possibly kind of track this what I've shown on the previous slide? How can we track things back in time? How can we actually find out what happened? How could we ever test this? Isn't this something that belongs in philosophy? Well, it turns out that actually it's not the case that it's philosophy. We do have almost relics. We've almost got photographs of what happened in the very early universe. And around the same time that Stephen Hawking and Roger Penrose were showing that Einstein's theory, implied that there was a very small, hot beginning to the universe, it was also realized that this very early, hot and dense universe basically leads to a relic background of microwaves, which basically fill all the universe around us. So the picture on the right-hand side from NASA shows you a kind of visualization of this. So that's the Earth. Of course, you can see Australia, you can see China there. And the Earth is sitting in a background of microwave radiation, which varies a little bit in temperature. So the blue bits are the cold bits and the red bits are the hot bits. And if you make detailed measurements of this radiation, you can get information about the early part of the universe. And in fact, around the time that Hawking and Penrose were developing their theoretical understanding, Wilson and Penzias discovered by accident this cosmic microwave background. So they were trying to do radio astronomy. So that was the receiver that you see on the top left. They were trying to do radio astronomy, and they just found that there was this annoying noise. They were getting frustrated because there just seemed to be some residual microwaves being received by the telescope, and they were frustrated because they were trying to look at stars which would emit radiation in microwave bands, and they were like, there must be some noise. They kind of eliminated all kinds of sources, And they started talking to the theorists and realized that they had discovered exactly this relic microwave background, which, as I said, is an immediate consequence of the early hot and dense universe that Hawking and Penrose had found. And so Penzias and Wilson won the Nobel Prize for this discovery. So it's much easier in a sense to win a Nobel Prize. Well, it's not an easy thing, but it's easier to win it as an experimentalist. If you're a theorist, the problem is that your theories have to be, for the Nobel Committee to give you the prize, your theories have to be really proven by experimental evidence. And that's quite challenging. A lot of the work that's done by theorists runs a long way ahead of experiments. And so it was not that, Einstein did not win the Nobel Prize in his lifetime for his theory of relativity. He won it for other things, but he didn't win it for relativity because there wasn't enough evidence for the relativity theory of gravity to be correct in its lifetime. So the prize for relativity actually was awarded after his lifetime to the experimentalists who discovered evidence for it. So what does this radiation look like? So over the last 20 to 30 years, the instrumentation has improved substantially. So we put, to measure this radiation, you've got to get away from the Earth because, Penzias and Wilson discovered it in their instruments, but they were right to worry that it might be contaminated by signals on Earth because there's all kinds of sources of microwaves. These days, I think it would be horrendous with all the mobile phones and wireless networks that we use. So to get away from the contamination on Earth, what you do is you send a probe up into space, and then you get the probe to actually measure the radiation that's all around it. About 30 years ago, the COBE probe shocked the scientific world by coming up with an image, which you can see on the left-hand side, which shows that the radiation has almost the same temperature, but it has small variations of being hot and being cold. When people saw that in the early 1990s, as I understand it, they found it astonishing that people could image this because it's actually the variation in temperature is 1 part in 10 to the 5 Kelvin. So it's a very, very small variation. But even 10 years later, the instrumentation had improved so that when WMAP went up into space, it got a much finer picture. So this is an image of exactly the same radiation, but you can see it showing much, much more detail. And then 10 years later, the Planck experiment went up, and you can see it gets even better again. And so over the last 20 to 30 years, we've had, such a detailed measurements of the temperature variations in the microwave background. And this really preserves a picture of what was going on in the very early universe. So this radiation is formed in the very early universe, and looking at that details, it's almost like looking at a kind of a picture of what was going on there. So the cosmic radiation, as I said, it preserves a snapshot of the universe. So it's a snapshot from 380,000 years old, but actually the variations of temperature in it were created much, much earlier. They were created within the first few seconds of the universe. So I worked on these subjects for maybe 20 years, but I still find remarkable that in a universe that is 13 billion years old, we can actually see back to the first few seconds of the universe. And so these small temperature variations really are associated with the formation of the structure of the universe as we see it, the stars and the galaxies. So in these pictures, wherever you see that something is hot, so it's shown as red, what that's reflecting is that there's a little bit more matter, there's a little bit more energy in those areas. And then gravity causes any excess of energy to basically collapse down to form stars and galaxies. So we can show this in this computer simulation. So you start in the top left corner, that's when the universe is at the earliest time. And you can see that there's just very, very small variations. So what we're plotting here is basically the hot spots of the cosmic microwave background. And then we let this evolve. We're running kind of codes to let this evolve with time. And you can follow it through. So you follow the top row and then the middle row and then the next row. And what happens is that the little sort of hotspots kind of attract things to it, and they start clustering together. And hopefully by the time you get to the sort of bottom line, you can see that that really does look very much like what you see when you look out on a clear night. That is the formation, that is basically the seeds from which stars and galaxies form. So these days there are many, many experiments which are probing the microwave background and other sources of information from the early universe. So some of them are telescopes which are based on Earth, and some of them are other very, very large-scale experiments. So the bottom right, that's a picture that some of you may have seen. That's an image of the experiments in CERN in Geneva. Those are the particle physics experiments where you smash beams of particles together, and they've got so much energy that they're reproducing the conditions of the early universe. So what's shown here is it's basically an aerial photo of Geneva, and the ring, of course, it's actually underground. It's buried in the Earth, but it's just to give you a scale of the size of the experiment that you need to actually get the energy for the particles to be like it was in the early universe. The top right is something that you may not have heard about. So this is an upcoming experiment with the European Space Agency and NASA having some collaboration with it. So this is to detect gravitational waves by detectors up in space. So you take 3 probes, which are sending laser beams to each other. So the red bars here are actually laser beams. Each of the arms of this experiment is 100,000 kilometers long, and the experiment is basically dragged along in orbit behind Earth. Now, if that sounds crazy to you, it also sounds crazy to me. I'm a theorist, not an experimentalist. I'm a mathematical physicist. We can actually do that is quite remarkable, but we can. So ESA, European Space Agency, have sent up the technology into space. It's working even better than design specifications. And this experiment is due to go up in the next 10 years. So we will have basically an arm of lasers being dragged around behind Earth, and this array will actually detect gravitational waves from the very beginning of the universe and from other types of gravitational waves as well. So I've mentioned the word gravitational waves. Again, this is something that you might have seen because it's got a lot of press in recent years. So immediately after Einstein wrote down his theory in 1915, he and others realized that it predicted the existence of gravitational waves, which are very much like just ordinary electromagnetic waves. They move at the speed of light. But he also predicted, it's very straightforward to sort of just do an estimate, that they would be really hard to measure. So a typical gravitational wave would be a kind of, in the scale of the Earth, something which is almost atomic size. So a gravitational wave passing through the Earth would typically move the surface of the Earth by a spacing as small as an atom. It's incredibly tiny. And so you have to get clever in your experiments. You have to look at very sophisticated ways to try and detect them. And it took 100 years. So they were detected by the LIGO experiment in 2015, and they won the Nobel Prize in 2017. So I should say our group in Southampton is part of that LIGO collaboration. And there are upcoming experiments, such as the one which I've shown on the previous slide, which will search for gravitational waves in the early universe, and we're also part of that experiment too. So from the mathematical physics side, from designing the data analysis, trying to understand what the shapes of the signals will actually look like. We're not involved in the actual building the equipment. So gravitational waves, another thing we do, again, to sort of fit with the experiments, is we kind of simulate what the gravitational waves will look like. So the kind of shape of the signal that you see in the detector is shown in the bottom here. But how do you get, how do you get that out of, how do you, associate that with some kind of process that's happening in astrophysics? So this is a simulation of 2 black holes. There are 2 black dots in the center of the picture, and the ripples that you see underneath are actually, they are illustrating how the black holes basically cause the space around them to ripple. So we said that things which are very heavy cause the space to kind of curve. Now, if the things are moving, that curvature kind of changes, and that's what causes a gravitational wave effect. So let me see if the simulation is going to work. There we go. So these things are moving around each other. So often in astrophysical systems, you will have 2 stars which are moving around them. Here, this is 2 black holes moving around each other, and they're getting closer and closer. And as they do, you can see that the shape, the distortions of the space around them is just huge, right? So it's just kind of getting points. Now they've kind of merged to form a single object, and now it's settling down to be much more like a spherical object, and it's just sending out ripples of gravitational waves. So one of the things we do, as I said, is we run simulations to actually produce those, to understand the shapes of those signals, because you need to know what you're looking for in your detectors. Now let's come to what LIGO actually found. So LIGO actually did discover exactly what I've just shown you, two black holes colliding with each other. And that's exactly what they saw. Okay, so what is shown here is, as in the graph, is the shape of the signal. Now you realize that it actually played as an audio file. That's because the frequencies of the gravitational waves are actually such that your ear could hear them. Now, the actual amplitude of the wave is just far too small. You know, your ears are bombarded all the time with gravitational waves, but they just, you know, the amplitude is just so small you can't hear it. So here we're basically accentuating the amplitude so you can hear it, but that's actually the sound that you would hear. So people often talk about listening to the universe. Different kinds of gravitational waves actually have different sort of shapes, sounds of signals. It's remarkable actually that your ear does an amazing job at picking out the features of the signal. So when we look at that shape of the signal, you might say, well, it looks a bit kind of, you know, messy. But when you listen to it with your ear, what you should have heard is that the pitch actually increased, particularly those of you who are musical, the pitch increased at the end of the signal. People refer to this often as a kind of like a chirp sound because it goes up in pitch at the end. And again, different kinds of gravitational waves have different sorts of sounds which your ear can resolve. So as I said, you know, it's a truly remarkable fact that we can actually trace back the beginning of the universe using all of these techniques. And in fact, we can get back to when it was 10 to the minus 39 seconds old. Again, as somebody who works in this area, I still find remarkable that for something that's 13 billion years old, we can actually figure out everything that was happening until 10 to the minus 39 seconds. But of course, you know, you say, well, what happens before 10 to the minus 39 seconds? You know, how did it actually begin, and how will it end? And that's the thing that's really at the forefront of modern research. It's saying what happened before 10 to the minus 39 seconds. It's mapping out in detail the very early universe. And it's sort of saying, you know, what will happen to the universe in the future. So it's developing and testing theories. So one of the theories that we work on is a very radical theory that at the beginning of the universe, inside black holes, when gravity is strong, space is so quantum that it effectively doesn't even seem as though we've got 3 dimensions of space. It's actually 2 dimensions. And if that sounds to you a bit crazy, and you know, it's a very radical idea. It's a lot of evidence for this idea being true now, but it's a very, you know, it's really a paradigm shift, because we're used to thinking of gravity and quantum forces as being very different. And what we're saying is that actually when gravity is very, very strong, in fact, it's better described as something which is in 2 dimensions, but more like a quantum atomic force. And I said that, you know, people have a modern scientific realization of the ancient ideas of yin yang. This is actually where we, well, as scientists, we probably misbehave, you know, we borrow the concepts in the wrong way. But this is the scientific realization that gravity in our 3-dimensional world, quantum forces, we think of them as being very different, but actually they're entwined, because as we go to the very beginning of the universe, we pass over from having a 3-dimensional world with gravity to having a world with 2 dimensions, but quantum forces. So the kinds of quantum theories that we have are the theories which were invented by the distinguished scientist Yang. So he won the Nobel Prize back in the 1950s for his work on the quantum theories for nuclear physics. So it turns out that these theories, not only could they be relevant for describing what's going on inside the nuclei of atoms, but these theories could actually describe the very, very early universe when space-time has only 2 dimensions, which is really quite remarkable. I think when he wrote on those theories in the 1950s, he would have found it, you know, crazy that these could describe the very beginning of the universe itself. As I said, when you work in theory, it's essential that you're actually making connections with experiments, and that's exactly what we're doing. So all these sort of very complex ideas, which I've skimmed over here, they make very specific predictions. So the temperature variations in the microwave background, which are being measured by satellites, these theories make specific predictions. What you have to do is actually test your theories against that. That's what we're doing. And you can see on the sort of chart on the right-hand side for the sort of test of the shape of the temperature variations, we tested against our theories, and indeed it seems to fit very well. There's still more to do. You still push further. You have a theory and you push it to its limits. You check it as much as you can, and really see what it can explain. So this concludes the sort of first part of the talk, where I'm sort of talking about fundamental science, and I'm going to sort of switch gears and go back to applications. And as I say, I really, one thing I really want to emphasize is that these go hand in hand. So the methods, the mathematics, the technology that you develop for scientific discovery feed into society, feed into the big issues in society, often in completely unanticipated ways. So I've already mentioned the big CERN experiments in Switzerland. Of course, they famously developed the World Wide Web because they had their collaborations were international. They had their researchers, working all around the world. They wanted a good way to kind of interface, to communicate between them. And it was, Tim Berners-Lee developed the World Wide Web exactly in that context, of course, with no foresight of how it would be used, 30 to 40 years later. Similarly, when you look at your mobile phone, I think it's also interesting to remember that a lot of that technology, the 3G technology in particular, was originally developed in the context of radio astronomy. So I showed you the picture of Penzias and Wilson, and I said that they were doing experiments in astronomy. They discovered by accident that the microwave radiation, but a lot of the technology that was developed in that context fed into the development of mobile phone technology. So as we come to the big questions in Stephen Hawking's book, so some of the things, as I said before, he raised artificial intelligence, the data science revolution. How will society change? What about communities that could be left behind, particularly in the global south? Global challenges, climate change, sustainability and energy, food security, population growth, healthcare and disease. And many of these questions may be things that you are particularly interested in, that you want to acquire skills so that you can actually join companies, join government agencies to actually help address those questions. So indeed, if we look for sort of common themes of what we do across the School of Mathematical Sciences, it's really mathematical modeling of processes, understanding, analyzing, and simulating data. Now, in the first half of this talk, I've talked about doing this for discovery, for fundamental science. But of course, the same kind of modeling, the same kind of analyzing and simulating data is being used for many applications, for healthcare, for medicine, for renewable energy, for actuarial forecasting, and for operational efficiency. So let me give you just what I'm going to do in the next part of the talk is really give you a sense of what we are doing in mathematical sciences and link it to some of the programs that we have. So actuarial forecasting, so this is really about forecasting in the context of insurance. So in the context of life actuarial science, people are thinking about mortality modeling for pensions, for life insurance, for governments to plan. There may be financial forecasting, corporate risk, stress testing, securities. And there's also actuarial forecasting for other kinds of insurance, for agricultural, for property, for marine. All of these things are obviously the topic of our MSc Actuarial Science program. So the kind of work that we do here, so our research work, so an example is our work with the Office for National Statistics in the UK, which would be advising both government and also insurance companies, so they'd be collecting data and analysing it. So mortality rates, accurate understanding of mortality rates, I think it's clear that they're essential to plan for pensions, to plan for how much a pension fund is going to have to pay out. And it's also essential when you're trying to work out life insurance premiums and pay what you're going to pay from your life insurance. Obviously, you're going to make your forecast based on the data that you have, but the data will, no data is perfect. There will always be gaps in it. And there will also be things which are just stochastic, random features. So Dr. Erin Dodd, who's one of the leaders of our actuarial program and her collaborators, been working for some years with the Office for National Statistics on smoothing this data. So what you see on the right-hand side is looking at the mortality rates, that's on the vertical axis, as a function of age. And it's, of course, incredibly important to get as accurate an estimate as possible of these mortality rates. So they use basically stochastic modeling techniques to understand and smooth the data. So you can see the Southampton models, give much more accurate forecasts than sort of the simplistic things, simplistic models that you get based on the crude data, which has all kinds of little glitches. You can see in the actual data that there'll be crosses which are slightly above, slightly below, essentially just because of random features. So this kind of smooth, it's called the smoothened life tables, are used by the Office for National Statistics, it's used by actuaries, it's used by government departments in their planning. Now, statistics is really playing a crucial role in many aspects of health and medicine. I think in the current context, we will all see, really statistics being discussed extensively in many corona-related contexts. For example, people talking about antigen and antibody tests. So a kind of a basic question, a basic sort of sense, what does it mean when we talk about reliability of tests? What does that mean in terms of being able to infer how many people have actually been infected? So this is one, it's not the only subject which is covered, but it's one of the subjects which you cover in our MSc statistics with applications to medicine. And we're very lucky in Southampton to have experts in this area. So in particular, we have an expert working on statistics in the context of drug testing for competitive sports. So as you all know, in competitive sports, obviously performance-enhancing drugs are banned. There will be substances which are shown to give an advantage are put on a banned list. And we know that athletes are regularly tested for evidence of using such drugs. There are very, very strict codes of conduct and rules. And you'll also probably be aware that if an athlete tests positive, this will sometimes be challenged. They will make a formal appeal, and they actually often be appealing on the grounds that I've sort of shown here, about the reliability of the test. They will try and say, well, this was actually a false positive, I'm completely innocent. It was some other kind of marker in my body that triggered this. So Professor Dankman-Bonning is one of the world's experts in this area. So he has developed a statistical analysis in the context of biomarker tests, working with experts in the sort of biosciences for actually constructing these tests. And they work for the World Anti-Doping Agency, which regulates the whole of the athletics world. They were aiming for a 1 in 10,000 false positive rate, and they have achieved that. And Professor Bonning has also been called as an expert witness in these cases where famous athletes test positive to actually give expert testimony about the reliability about these of these tests. So I'm very, very conscious we have in our panelists here an expert in optimization, and I hope you'll be happy with what I'm going to say here. So we're very proud in Southampton to have a really, really strong research group in operational research, working in optimization. And so the basic idea is that you use optimization to make decisions in the context of manufacturing, transportation, scheduling, policy model, and business, also healthcare, I'll come to in a moment. So, the basic idea is that you're trying to take a real world problem and you're trying to use mathematical modeling to actually provide the best possible solutions to the real world problem. This is something which you learn about in the MSc Operational Research and in the Data Decision Analytics. And as I said, we have a very, very strong group in this area who work with a large number of external partners. I've just given a handful of highlights here and a handful of what they do. So Professor Jörg Vlieger has worked with the European Space Agency. I mentioned them previously in the context of putting gravitational wave experiments up in space. But of course, actually getting things into space has its own huge kind of challenges. And Jörg has worked with them about optimizing the trajectories. So you basically want to get your load up into space for the minimum cost, the maximum accuracy. That's clearly a mathematical optimization problem. So you see sort of shown on the bottom right, illustration of some of the work that he's actually done there. We also work with a large number of companies, including Virgin, BAA, Carnival, Siemens, Northrop Grumman. What's shown on the top here is some of the work that Christine Curry has done with boat companies, with ferry companies. So again, there's a kind of an optimization problem here, that when they are loading onto boats, they want to get as much onto the boat as possible. They want it to get on and off the boat as fast as possible. And so what you see shown on the top right is the sort of, the kind of the packing problem of how you get sort of large and small things and you pack it optimally. What you see on the top left is one of the ferry companies with whom she works. It's actually, for those in the Southampton area, it's a very, very familiar company because they actually do ferries across from the south coast into the neighbouring area of the Isle of Wight. Another important aspect of the work done in our operational work research group is in the context of healthcare modelling. So many different aspects of this obviously playing a hugely important role at the current time. So modelling patient flow to optimise the use of resources. At the current time, this expertise is being used particularly to optimise and make the best use that we can of intensive care facilities. That's for patients who need very specialised care. There are also, of course, supply chain logistics issues coming into healthcare, and there's also infectious disease modelling. So this is, again, something that in the recent context we are, very much familiar with. So the kinds of things that you do here, I should say, this is just some slides from some of the things that I've been doing. Myself. So people are trying to analyze the data on COVID cases. I've already referenced the fact that data has gaps, it has sort of glitches in it. So you're trying to kind of smoothen the data, and that's what's shown to you on the bottom right that I'm doing with the cases of COVID in New York. The actual cases are dotted there, and then they're sort of smoothened. You use, both cases and hospital admissions. You basically combine the data to make the most accurate estimate that you can of how the transmission rate is, and that's shown on the top right. So that's actually a combination of data on new cases, data on hospital occupancy, hospital admissions, to actually see how the transmission rate of the disease is changing with time. It's the all-important factor of 1. So if the reproducibility factor is less than 1, the disease is not growing. If it's greater than 1, then actually we're in a kind of an exponential growth phase. And of course, the other thing that many of us are doing, operational research group and other parts of mathematical sciences too, are projections and forecasts in the context of developing strategies for exiting lockdown. And again, the top left-hand side, you see these are kind of projections of, how much the number of cases will fall depending on the length of the lockdown. What would be, if you're going to have multiple lockdowns, what would be the optimal gap between the lockdowns? So I've already, in a sense, inferred to it. A lot of what we're doing is really in the general themes of data analytics. It's inspecting, it's cleaning, it's modeling data, you're discovering information, you're getting information to support decision making. So we're combining statistics, machine learning, mathematical modeling, programming, all of these aspects into it. And it's really covered across the MSc programs and statistics, OR, data and decision analytics, with particular sort of specializations in each of those different areas. In terms of data analysis, I think it's interesting to say that, in problems which look seemingly very, very different, you have often very similar techniques coming into play. So on the left-hand side, I'm showing you a picture I showed you earlier, which was really a simulation coming from a simulation of the very early universe. It's coming from the formation of galaxies, and you see these sort of little branches of the formation of galaxies. What's shown on the right-hand side is completely different data. So this is data about patients who have asthma. It's genetic data about patients who have asthma. And I put both pictures there to sort of say that as you look at this visualization, your eye is almost drawn to sort of finding patterns and shapes within that data. And this is indeed correct. There's a whole mathematical formulation of this to actually look at the shapes within the data. Shapes is characterized in a branch of mathematics called topology. And so topological data analysis can be used in both cases to actually understand the underlying sort of information that's contained in this data. So as I said, two seemingly completely different questions that you're asking. One is about the evolution of galaxies. The other is looking for patterns in patients who have asthma. Actually, you can use very similar mathematical techniques. And in the latter context, in the context of patients who have asthma, Professor Jacek-Brodsky has been working with the university hospitals. So Professor Brodsky is an expert in topology, and he has been working with the University Hospital in Southampton about trying to analyze this gene expression data to actually pick out the underlying features. So identify genes associated with specific types of specific kinds of asthmatic disease. So a final sort of example of some of the ways in which we're using mathematics to address big challenges. So the UK government is investing heavily in research to address key challenges. One of the challenges they've identified is the need for sustainable, for renewable energy. And they've established a national collaboration called Faraday, which works in particular on the design and development and manufacture of the next generation of batteries. So the picture on the right-hand side, again, it's an image that comes from sort of experiments. It's actually what you would see if you looked at detail inside the battery of your phone as your battery starts to degrade. If you're using an Apple phone and it starts saying that your battery only has 90% life, if you actually looked in the detail, this is what you would tend to see. So the bit at the bottom gray area is actually the metal collector. And the electrode particles, the things which are actually really functioning to carry a current, those are actually white. And you can see in this picture that they've basically broken into little tiny granules. This is kind of degrading. So one of the big problems is to actually model batteries, particularly how they degrade. There's many aspects of how they degrade, that things crack, that the material actually stops being active, that it kind of crumbles to pieces. And we have people working on this multi-scale modeling. And again, it's interesting to know that we're using and combining different mathematical techniques. We have multiple scales in the problem, multiple time scales, multiple physical scales in the problem, and there are many agents involved, many things which are kind of causing the impacts on the batteries. So that was my brief tour of some of the highlights of things that we do in mathematical sciences. So let me sort of wrap up with a summary of it. So the big questions that are posed in science and in society, mathematical sciences provides a really big role in answering those questions. Questions, from the beginning of the universe to the challenges faced in society, the techniques that we use, the sort of detailed modeling of phenomena, the use of data to kind of extract new information, to feed it back and improve our models, these techniques are used for all of these big questions. In terms of the skills that you get by studying mathematical sciences, so the skills in modeling, in data analytics, and statistical analysis, they are all really highly sought after. So our students, when they come out of these programs, can actually really receive many offers from many different companies and many different agencies, and they have many different paths that they can go under. So thank you very much.